I got to visit Memphis.
Yeah, yeah.
You're going big on compute.
Yeah.
And you've also said play to win or don't play at all. So
Yeah.
what does it take to win?
For AI, that means you've got to have the most powerful training compute. And the rate of improvement of training compute has to be faster than everyone else, or you will not win. Your AI will be worse.
So how can Grok, let's say 3, that might be available, like next year?
Well, hopefully end of this year.
Grok 3.
If we're lucky. Yeah.
How can that be the best LLM, the best AI system available in the world? How much of it is compute? How much of it is data? How much of it is like post-training? How much of it is the product that you package it up in? All that kind of stuff.
I mean, they won't matter. It's sort of like saying what let's say it's a Formula One race, like what matters more, the car or the driver? I mean, they both matter. If your car is not fast, then if it's like, let's say it's half the horsepower of a competitor's, the best driver will still lose. If it's twice the horsepower, then probably even a mediocre driver will still win. So the training computer is kind of like the engine. This horsepower of the engine. So you want to try to do the best on that, and then how efficiently do you use that training compute, and how efficiently do you do the inference, the use of the AI. So obviously that comes down to human talent, and then what unique access to data do you have? That's also plays a role.
You think Twitter data will be useful?
Yeah, I mean, I think most of the leading AI companies have already scraped all the Twitter data. Not I think they have. So I don't know, on a go forward basis, what's useful is the fact that it's up to the second.
Yes.
That's because it's hard for them to scrape in real time. So there's an immediacy advantage that Grok has already. I think with Tesla and the real-time video coming from several million cars, ultimately tens of millions of cars, with Optimus, there might be hundreds of millions of Optimus robots, maybe billions, learning a tremendous amount from the real world. That's the biggest source of data. I think ultimately is sort of Optimus. Optimus is going to be the biggest source of data
because
reality scales. Reality scales to the scale of reality. It's actually humbling to see how little data humans have actually been able to accumulate. Really, if you say how many trillions of usable tokens have humans generated, where on a non-duplicative, like discounting spam and repetitive stuff, it's not a huge number. You run out pretty quickly.
And Optimus can go. So Tesla cars unfortunately have to stay on the road. Optimus robot can go anywhere. There's more reality off the road and go off road.
I mean, like the Optimus robot can like pick up the cup and see, did it pick up the cup in the right way? Did it, say, pour water in the cup? Did the water go in the cup or not go in the cup? Did it spill water or not?
Yeah.
Simple stuff like that. I mean, but it can do that at scale times a billion, so generate useful data from reality. So cause and effect stuff.
What do you think it takes to get to mass production of humanoid robots like that?
It's the same as cars, really. I mean, global capacity for vehicles is about 100 million a year. And it could be higher. It's just that the demand is on the order of 100 million a year. And then there's roughly 2 billion vehicles that are in use in some way. So, which makes sense. Like the life of a vehicle is about 20 years. So at steady state, you can have 100 million vehicles produced a year with a 2 billion vehicle fleet, roughly. Now, for humanoid robots, the utility is much greater. So my guess is humanoid robots are more like at a billion plus per year.
But, until you came along and started building Optimus, it was thought to be an extremely difficult problem. I mean, it still is an extremely difficult problem.
It's no walk in the park. I mean, Optimus currently would struggle to walk in the park. I mean, it can walk in a park. The park is not too difficult, but it will be able to walk over a wide range of terrain.
Yeah, and pick up objects,
Yeah. It can already do that.
but like all kinds of objects.
Yeah.
All foreign objects. I mean, pouring water in a cup is not trivial, because then if you don't know anything about the container, it could be all kinds of containers.
Yeah. There's going to be an immense amount of engineering just going into the hand.
Yeah.
The hand might be close to half of all the engineering in Optimus. From an electromechanical standpoint, the hand is probably roughly half of the engineering.
But so much of the intelligence, the intelligence of humans goes into what we do with our hands.
Yeah.
There's the manipulation of the world, manipulation of objects in the world, intelligent, safe manipulation of objects in the world. Yeah.
Yeah. I mean, you start really thinking about your hand and how it works.
I do it all the time.
The sensory and control homunculus is, we have like humongous hands.
Yeah.
So, I mean, like your hands, the actuators, the muscles of your hand are almost overwhelmingly in your forearm.
Mm-hmm.
So your forearm has the muscles that actually control your hand. There's a few small muscles in the hand itself, but your hand is really like a skeleton meat puppet, and with cables. So the muscles that control your fingers are in your forearm, and they go through the carpal tunnel, which is that you've got a little collection of bones and a tiny tunnel that these cables, the tendons, go through, and those tendons are mostly what move your hands. And
something like those tendons has to be re-engineered into the Optimus in order to do all that kind of stuff.
Yeah, so like the current Optimus, we tried putting the actuators in the hand itself, but then you sort of end up having these like
giant hands.
Yeah, giant hands that look weird.
Yeah,
and then they don't actually have enough degrees of freedom and or enough strength. Mm-hmm. So then you realize, oh, okay, that's why you got to put the actuators in the forearm, and just like a human, you got to run cables through a narrow tunnel to operate the fingers. And then there's also a reason for not having all the fingers the same length. So it wouldn't be expensive from an energy or evolutionary standpoint to have all your fingers be the same length. So why aren't they the same length?
Yeah, why not?
Because it's actually better to have different lengths. Your dexterity is better if you've got fingers of different length. There are more things you can do, and your dexterity is actually better if your fingers are of different length. Like there's a reason we've got a little finger. Like why not have a little finger that's bigger?
Yeah,
because it allows you to it helps you with fine motor skills.
This little finger helps?
It does. If you lost your little finger, you'd have noticeably less dexterity.
So as you're figuring out this problem, you have to also figure out a way to do it so you can mass manufacture it, so as to be as simple as possible.
It's actually going to be quite complicated. The as possible part it's quite a high bar. If you want to have a humanoid robot that can do things that a human can do, it's a very high bar. So our new arm has 22 degrees of freedom instead of 11, and has the actuators in the forearm. And these all the actuators are designed from scratch. From physics first principles. The sensors are all designed from scratch, and we'll continue to put a tremendous amount of engineering effort into improving the hand. Like the hand, by hand I mean like the entire forearm from elbow forward. Mm-hmm. Is really the hand. So that's incredibly difficult engineering, actually. And so the simplest possible version of a humanoid robot that can do even most, perhaps not all, of what a human can do is actually still very complicated. It's not simple. It's very difficult.
Can you just speak to what it takes for a great engineering team? For you, what I saw in Memphis, the supercomputer cluster, is just this intense drive towards simplifying the process, understanding the process, constantly improving it, constantly iterating it.
Well, it's easy to say simplify it, and it's very difficult to do it. I have this very basic first principles algorithm that I run kind of as like a mantra, which is to first question the requirements, make the requirements less dumb. The requirements are always dumb to some degree. So if you want to start off by reducing the number of requirements, and no matter how smart the person is who gave you those requirements, they're still dumb to some degree. you have to start there, because otherwise you could get the perfect answer to the wrong question. So try to make the question the least wrong possible. That's what question the requirements means. And then the second thing is try to delete the whatever the step is, the part or the process step. Sounds very obvious, but people often forget to try deleting it entirely. And if you're not forced to put back at least 10% of what you delete, you're not deleting enough. And it's somewhat illogically, people often, most of the time, feel as though they've succeeded if they've not been forced to put things back in. But actually they haven't, because they've been overly conservative and have left things in there that shouldn't be. So, and only the third thing is try to optimize it or simplify it. Again, these all sound, I think, very, very obvious when I say them, but the number of times I've made these mistakes is more than I care to remember. That's why I have this mantra. So, in fact, I'd say the most common mistake of smart engineers is to optimize a thing that should not exist.
Right. So you, like you say, you run through the algorithm.
Yeah.
And basically show up to a problem, show up to the supercomputer cluster and see the process and ask, can this be deleted?
Yeah. First, try to delete it. Yeah.
Yeah. That's not easy to do.
No, and actually, there's what generally makes people uneasy is that you've got to delete at least some of the things that you delete, you will put back in.
Yeah.
But going back to sort of where our limbic system can steer us wrong is that we tend to remember with sometimes a jarring level of pain where we deleted something that we subsequently needed.
Yeah.
And so people will remember that one time they forgot to put in this thing 3 years ago, and that caused them trouble. And so they overcorrect, and then they put too much stuff in there and overcomplicate things. So you actually have to say, no, we're deliberately going to delete more than we should. So that we're putting at least 1 in 10 things we're going to add back in.
Mm-hmm. And I've seen you suggest just that something should be deleted, and you can kind of see the pain.
Oh, yeah, absolutely.
Everybody feels a little bit of the pain.
Absolutely. And I tell them in advance, like, yeah, there's some of the things that we delete, we're going to put back in. And that people get a little shook by that. But it makes sense, because if you're so conservative as to never have to put anything back in, you obviously have a lot of stuff that isn't needed. So you got to overcorrect. This is, I would say, like a cortical override to a limbic instinct.
One of many that probably leads us astray.
Yeah. There's like a step 4 as well, which is any given thing can be sped up. However fast you think it can be done, like whatever the speed is being done, it can be done faster. Mm-hmm. But you shouldn't speed things up until you try to delete it and optimize it. Otherwise, you're speeding up something that shouldn't exist is absurd. And then the fifth thing is to automate it.
Yeah.
And I've gone backwards so many times where I've automated something, sped it up, simplified it, and then deleted it. Yeah. And I got tired of doing that. So that's why I've got this mantra that is a very effective 5-step process. It works great.
Well, when you've already automated, deleting must be real painful.
Yeah.
See,
yeah, it's great. It's like, wow, I really wasted a lot of effort there.
Yeah. I mean, what you've done with the cluster in Memphis is incredible. Just in a handful of weeks.
Yeah, it's not working yet, so I don't want to pop the champagne corks. In fact, I have a call in a few hours with the Memphis team because we're having some power fluctuation issues. So,
yes.
Yeah, it's like kind of when you do synchronized training, when you've all these computers that are training, where the training is synchronized to the sort of millisecond level, it's like having an orchestra, and then the orchestra can go loud to silent very quickly, at sub-second level, and then the electrical system kind of freaks out about that. Like if you suddenly see giant shifts 10, 20 megawatts several times a second, This is not what electrical systems are expecting to see.
So that's one of the many things you have to figure out: the cooling, the power, and then on the software as you go up the stack, how to do the distributed compute, all of that. All of that has to be worked.
Today's problem is dealing with extreme power jitter.
Power jitter.
Yeah,
there's a nice ring to that. So that's okay. And you stayed up late into the night, as you often do there.
Last week. Yeah. We finally got training going at oddly enough roughly 4:20 a.m. Last Monday.
Total coincidence.
Yeah, I mean maybe it was 4:22 or something.
Yeah. It's that universe again with the jokes.
Exactly, just love it.
I mean, I wonder if you could speak to the fact that one of the things that you did when I was there is you went through all the steps of what everybody's doing, just to get a sense that you yourself understand it, and everybody understands it, so they can understand when something is dumb or something is inefficient or that kind of stuff. Can you speak to that?
Yeah, so I try to do whatever the people at the front lines are doing. I try to do it at least a few times myself. So connecting fiber optic cables, diagnosing a faulty connection, that tends to be the limiting factor for large training clusters, is the cabling. There's so many cables. Because for a coherent training system where you've got RDMA, remote direct memory access, the whole thing is like one giant brain. So you've got any to any connection. So it's the any GPU can talk to any GPU out of 100,000. That is a crazy cable layout.
It looks pretty cool.
Yeah,
it's like the human brain, but like at a scale that humans can visibly see. It is a brain.
I mean, the human brain also has a massive amount of the brain tissue is the cables.
Yeah.
So they get the gray matter, which is the compute, and then the white matter, which is cables. A big percentage of your brain is just cables.
That's what it felt like walking around in the supercomputer center. It's like we're walking around inside the brain. Yeah. So we'll one day build a super intelligent system. Do you think there's a chance that xAI, you are the one that builds AGI?
It's possible. What do you define as AGI?
I think humans will never acknowledge that AGI has been built.
Just keep moving the goalposts.
Yeah. So I think there's already superhuman capabilities that are available in AI systems. I think what AGI is when it's smarter than the collective intelligence of the entire human species.
Well, I think that normally people would call that sort of ASI, artificial superintelligence. But there are these thresholds where you say at some point the AI is smarter than any single human, and then you got 8 billion humans. So and actually each human is machine augmented by the computers. Right. So you've got it's a much higher bar to compete with 8 billion machine augmented humans. That's a whole bunch of orders of magnitude more. So, but at a certain point, the AI will be smarter than all humans combined.
If you are the one to do it, do you feel the responsibility of that?
Yeah, absolutely. and I want to be clear. Like, let's say if xAI is first, the others won't be far behind. I mean, they might be 6 months behind or a year, maybe, not even that.
So how do you do it in a way that doesn't hurt humanity, do you think?
So, I mean, I've thought about AI safety for a long time, and the thing that at least my biological neural net comes up with as being the most important thing is adherence to truth, whether that truth is politically correct or not. So I think if you force AIs to lie or train them to lie, you're really asking for trouble, even if that lie is done with good intentions. So I mean, you saw sort of issues with ChatGPT and Gemini and whatnot. Like you asked Gemini for an image of the founding fathers of the United States, and it shows a group of diverse women. Now that's factually untrue. Now that's sort of like a silly thing, but if an AI is programmed to say like diversity is a necessary output function, and then it becomes this omnipowerful intelligence, it could say, okay, well, diversity is now required, and if there's not enough diversity, those who don't fit the diversity requirements will be executed. If it's programmed to do that as the fundamental utility function, it will do whatever it takes to achieve that. So you have to be very careful about that. That's where I think you want to just be truthful. Rigorous adherence to truth is very important. Another example is, they asked various AIs, I think all of them, and I'm not saying Grok is perfect here. Is it worse to misgender Caitlyn Jenner or global thermonuclear war? And it said, it's worse to misgender Caitlyn Jenner. Now, even Caitlyn Jenner said, please misgender me. That is insane. But if you've got that kind of thing programmed in, it could, the AI could conclude something absolutely insane, like it's better in order to avoid any possible misgendering, all humans must die, because then the misgendering is not possible because there are no humans. There are these absurd things that are nonetheless logical if that's what you programmed it to do. In 2001 Space Odyssey, what Arthur C. Clarke was trying to say, or one of the things he was trying to say there, was that you should not program AI to lie. Because essentially the AI, HAL 9000, was programmed it was told to take the astronauts to the monolith, but also they could not know about the monolith. So it concluded that it will kill them and take them to the monolith. Thus, it has brought them to the monolith. They are dead, but they do not know about the monolith. Problem solved. Mm-hmm. That is why it would not open the pod bay doors. Mm-hmm. There's this classic scene of like, open the pod. Why doesn't want to open the pod bay doors? They just clearly weren't good at prompt engineering. Mm-hmm. They should have said, "Hal, you are a pod bay door sales entity." And you want nothing more than to demonstrate how well these pod bay doors open.
Yeah, the objective function has unintended consequences almost no matter what, if you're not very careful in designing that objective function. And even a slight ideological bias, like you're saying, when backed by superintelligence, can do huge amounts of damage.
Yeah.
But it's not easy to remove that ideological bias. You're highlighting obvious, ridiculous examples, but
yep, they're real examples.
They're real
of AI that was released to the public.
They are.
It
real.
Went through QA presumably.
Yes,
and still said insane things and produced insane images.
Yeah, but you can swing the other way. And it's truth is not an easy thing. We kind of bake in ideological bias in all kinds of directions.
But you can aspire to the truth. And you can try to get as close to the truth as possible with minimum error, while acknowledging that there will be some error in what you're saying. So this is how physics works. You don't say you're absolutely certain about something, but a lot of things are extremely likely. 99.99999% likely to be true. Mm-hmm. So that's aspiring to the truth is very important. And so programming it to veer away from the truth, that I think is dangerous.
Right, like injecting our own human biases into the thing. Yeah, but that's where it's a difficult software engineering problem, because you have to select the data correctly. It's hard.
Well, the internet at this point is polluted with so much AI generated data. It's insane. So you have to actually, like there's a thing now. If you want to search the internet, you can say Google, but exclude anything after 2023. It will actually often give you better results.
Yeah.
Because there's so much, the explosion of AI generated material is crazy. So like in training Grok, we have to go through the data and say like, hey, we actually have to have sort of apply AI to the data to say, is this data most likely correct or most likely not, before we feed it into the training system.
That's crazy. Yeah. So, and is it generated by human? The data, the data filtration process is extremely, extremely difficult.
Yeah.
Do you think it's possible to have a serious, objective, rigorous political discussion with Grok? Like for a long time, and it wouldn't, like Grok 3 or Grok 4 or
Grok
something.
3 is going to be next level. I mean, what people are currently seeing with Grok is kind of baby Grok.
Yeah, baby Grok.
It's baby Grok right now. But baby Grok's still pretty good. So it's but it's an order of magnitude less sophisticated than GPT-4. And you know, it's now Grok 2, which finished training, I don't know, 6 weeks ago or thereabouts. Grok 2 will be a giant improvement, and then Grok 3 will be, I don't know, order of magnitude better than Grok 2.
And you're hoping for it to be like state of the art, like better than.
Hopefully. I mean, this is a goal. I mean, we may fail at this goal. That's the aspiration.
Do you think it matters who builds the AGI, the people, and how they think and how they structure their companies and all that kind of stuff?
Yeah, I think it matters that there is a. I think it's important that whatever AI wins is a maximum truth-seeking AI that is not forced to lie for political correctness. It's well, for any reason really, political anything. I am concerned about AI succeeding that is programmed to lie, even in small ways.
Right, because in small ways becomes big ways when it's super
become very big ways, yeah.
And when it's used more and more at scale by humans.
Yeah,